In this video, we're going to learn about isotopes. Previously, we talked about ions, which are atoms that have either lost or gained electrons. So if you have something like calcium and it loses an electron or two, it becomes calcium plus 2. Or oxygen would gain 2 electrons, it becomes negative 2. So ions are different because they have different electrons, so E negative for electrons. Isotopes, however, are atoms of the same element that have different masses, and this is due to the neutrons. Because remember that mass equals the number of neutrons plus the number of protons. You can't change the protons because then you change the element, but if you change the neutrons, you change the mass. For example, here we have hydrogen. If you look at your periodic table, hydrogen is atomic number 1, meaning that it has 1 proton. If you look at the mass, it's slightly over 1, which means that on average, a normal atom of hydrogen has 0 neutrons. That 1 proton accounts for all of its mass. However, there are different isotopes of hydrogen that have a mass of 2 or a mass of 3. So in this case, we have 0 neutrons. Here we have 1 neutron, and here we have 2 neutrons. So the number of protons plus the number of neutrons equals the mass. So in each of these, we have 1 additional neutron. They're all still hydrogen, but you can see that they have different masses. This doesn't really change how they react with things, because that's determined by the electrons, which we'll talk about at a later time, but these are differences between atoms of the same element. So here, just to get you in the habit of writing possible symbols for isotopes, we're going to use the letter designation from the periodic table, so whatever the element happens to be. So for our first one, we'll do potassium. If you find potassium over here at atomic number 19, you'll see that the weighted average mass is a little over 39. Meaning that most of the isotopes are going to have a mass of 39. So in order to show this in isotopes notation, we would write the letter of the symbol, a dash, and then the whole number mass number, in this case 39. So K39 would be one isotope, and then since it's a little over 39, a next possible isotope would be 1 more additional neutron, so we add 1 to that, and we would get something like K40. Now this may or may not be a possible isotope. We don't know that without looking it up, but for now that's a possibility, because the weighted average, 39.0983, should be somewhere in the middle of the other possible isotopes. And we'll do a worksheet where we practice lots of these for lots of different elements, so no worries so far. Our next one, carbon. Find carbon on the periodic table, atomic number 6, and we see that it has a mass of 12.0111. So our first possible isotope is going to be closest to that, C12 for carbon 12. We want to go a little bit above that to get 1 more neutron, so we'd have C13. And in fact, there is indeed a C14. This one, however, is radioactive, meaning that it's not stable, so there's a very, very small percentage of this. So typically when we look at the weighted average of carbon, we're only looking at the 12 and 13, and that's what we'll calculate on the next slide. So we'll ignore this for now and just look at our carbon 12 and carbon 13. So as we said before, the atomic mass is the number of protons and the neutrons, which would give us a whole number. This we only get when we're looking at 1 atom. However, when we take into account all of the atoms, we're going to have some weighted average mass, because we have to look at all of the different isotopes. So for carbon, as we just said, there's carbon 12 and carbon 13. These shown with the masses in the top left corner, like we normally do for atomic symbols. Now, if these were evenly matched, such that there was 50% carbon 12 and 50% carbon 13, you could just take the average and say that the average was 12.5, AMU. However, in reality, if you had 100 grams of carbon sample, 98.9% of that would be carbon-12, and the other 1.1% of the atoms would be carbon-13. So carbon is going to be influenced much more by the atoms with a mass of 12 than by the atoms with a mass of 13. So this is a weighted average, just like your grades are a weighted average. Homework is a certain percentage, labs and quizzes are a certain percentage, tests are a certain percentage. They don't all count the same, so you can't just add up all the numbers and divide them by however many different sections you have. You have to take into account what they're weighted. In this case with isotopes, in order to determine this weighted average mass, we have to take the percent abundance here, which is what this percent means. 98.9% of the samples will be carbon-12, and we multiply it by the mass. Now, percent really means per 100. So in order to put these into a calculation we can use, we just move the decimal place 2 points, and we get what's called our relative abundance. So this is our percent abundance here. When we divide that by 100, move the decimal over, we get 0.989. This is relative abundance. Nothing different. This one you can just put into your calculator more easily than this because you'd have to divide by 100. So we take the relative abundance of our first isotope, in this case carbon-12, so 0.989. Then we simply multiply it by the mass, 12. Now we're going to do the same thing for our next isotope. We have 1.1% carbon-13. Dividing this by 100, remember that there's going to be another 0 in the place here, so we have to put it in front. If you only moved it 1, we would have what looked like 11%, and you can't add these two together and get 100. Right? The total percent of the atoms has to add up to 100. So we take our 0.011 relative abundance, multiply it by the mass of carbon-13, and when you do that, you get 12.011 AMU, and compare that to the number on the periodic table, which is 12.0111. So this number probably includes the very small percentage of carbon-14. Like I said, we will do some practice with this where we calculate the weighted average mass of a lot of different elements, and we'll compare those to the values on the periodic table. If this had more isotopes, we would do the same thing. We would take the relative abundance times the mass. Doesn't matter how many isotopes you have, whether it's 2 or it's 200. You do the same exact thing. Just all of your percentages would add up to 100. All of your relative abundances would add up to 1.